I'm going to be talking to you guys today about real-time orbit and atmospheric drag estimation for spacecraft swarms, which is the work I've been working on the last couple of quarters. Okay, so standard presentation overview. Here's Phoebe splashing in a puddle. Okay, so what am I talking about? Atmospheric drag is the largest source of orbit uncertainty in Leo. This is a trope in papers in this field that the first sentence of these papers is always some variation of this. And that's a problem, especially now, because the use of differential atmospheric drag or even absolute atmospheric drag for control is becoming increasingly popular. A couple of examples: Planet Labs uses atmospheric drag for phasing. SwarmX is an upcoming mission that will use differential drag for control. And this high uncertainty causes problems. Famously, SpaceX lost 40 Starlink satellites right after deployment because of a very minor geomagnetic storm, which I've shown the KP index here on the right. So the little burst of yellow there at the left is the storm that resulted in the loss of those satellites. So actually quite minor compared to some storms. This is the March 2015 St. Patrick's Day geomagnetic storm, which was quite substantial. So the problem that we're trying to solve here is that I'm not going to address the absolute case as much, but the problem is really that spacecraft swarms need to know accurate information about the drag environment in order to do relative orbit control. And that information, which is reasonable enough that they would actually take a control action based on it, right? If you have a very, very high uncertainty, you may decide not to take a control action because of that. And we want to mitigate that. So what am I talking about? Atmospheric drag. Let's break down each of the components. This is the standard equation you'll see for atmospheric drag in basically any context. So CD, the coefficient of drag. This is tricky to nail down. This has been a topic of intense research for decades in the space domain, basically for satellites. And the value of CD is the result of a complex interaction between spacecraft shape, the attitude, material properties, the molecular constituents at the chosen altitude. This is varying relatively slowly over time as the surface properties change as well. And it's very difficult to model accurately. Cross-sectional area. So this also varies. This can vary quite rapidly over time, limited only to spacecraft dimension and its ability to slew. And this can be known relatively accurately if you have a good model of your spacecraft shape and knowledge of your attitude. Mass varies over time due to propellant expenditure. This can be known with reasonable accuracy if you have an initial measurement based on an on-ground calibration, and you can potentially update it in flight based on the performance of known maneuver and the magnitudes of those maneuvers. So this, like coefficient drag, is another tricky one. This one varies a lot during a single orbit and also over time due to varying solar activity. This is extremely challenging to model and predict. The little figure here on the right shows the same orbit, but at two different times. So one is in 2001 at a period of high solar activity, and one is 7 years later during a period of low solar activity. So you see there's a variability of almost 2 orders of magnitude in atmospheric density for the same orbit. And finally, the relative velocity. So the bulk component of the relative velocity is based on Earth's rotation. And that part is easily modeled and well understood. The challenge is the delta, where the wind in the upper atmosphere is extremely complex and also very poorly understood. And so typically in real space applications, we just ignore the wind and add process noise, basically. Okay, so what is actually needed for this? Right? Want to focus our efforts on some requirement, especially if we're working on a flight mission, some requirement for that mission. And thankfully for me, I can simply refer to Matthew's papers, which tell me that this control action is represented by this equation. And so you see delta beta rho, as he terms it. I use slightly different terminology, but we call this the augmented ballistic coefficient. It's the product of density and the ballistic coefficient. That's what is needed to understand what that U is going to be. And so in addition to considering what is needed by control, I also need to think about what are the limitations of miniaturized distributed space systems. And those are things we all know about, right? Needs to be low computational cost, needs to be not require additional hardware. And so from this, we formulate a concise problem statement, which is obtain accurate real-time information about relative atmospheric drag experienced by spacecraft must have low computational cost, require no specialized hardware, and be performed autonomously. So quickly, the current state of the art, basically this has been a problem since Sputnik, and all of the approaches can essentially be divided into one of three things: measurement, modeling, or estimation. Measurement it can be a direct or indirect measurement. There's a lot of flight heritage for this. For example, Grace and Champ both used very high accuracy accelerometers to try to basically disambiguate this from the other unmodeled perturbations. The LISA Pathfinder mission, this one was really cool, flew a shielded proof mass, where basically you have a shield around a free-floating craft around that mass as it's moving through the atmosphere. So in that way, you get a drag-free trajectory. And then IMX Explorer 2 did sort of a direct measurement, which has instruments which can directly sample temperature and atmospheric composition and use that to then, from a physics-based model, back out what's the density. And there's been a variety of other methods proposed requiring specialized hardware. Spatula is a fun one. It's a CubeSat with just basically a spatula attached to it, and it measures drag torque. Advantages to this are you get real-time or near real-time data about atmospheric drag, and they can be extremely high accuracy. The disadvantage, of course, is its dependence on specialized hardware, and so that rules it out for us. Modeling is the other way. So there are many, many models. Probably the MSIS and Jackia families are very well known. Harris-Priester is also very well known. There are tons of these. Typically, they require an input to them, which is, in addition to your spacecraft position, they need these geomagnetic indices. So the most common are KP, AP, and F10.7. KP and AP are essentially the same. Just one is log scale and one is linear scale. And F10.7 is a flux measurement of radio transmissions from the sun. Advantages of these models are that static models like Harris-Priester can be super fast to evaluate, so that's typically what's used on board. Dynamic models can be very accurate, but only ex post facto. So these NRL-MSIS, Jackia models, they can be used ex post facto based on observations of solar activity and give a good picture of what was happening in the atmosphere at a specific time. This is what ends up getting used in ground truth simulations. Disadvantages are that static models like Harris-Priester can have very large errors. Dynamic models are dependent on these indices. They're very bad at prediction, and they place a burden on operators. If you're trying to use them in flight, your operator needs to provide updated indices at a steady pace. Otherwise, the model doesn't work. And then lastly, estimation alongside the orbit itself. So usually what is done in this is authors will try to estimate some sort of global neutral density, sometimes based on constellations, sometimes based on just a few spacecraft, but in very different orbits. Starlink spacecraft, they estimate their ballistic coefficient and also a drag proxy, essentially the product of, they take out the ballistic coefficient and then you're left with the 1/2 rho v squared portion. That's what their proxy is. But they don't publish their data. And at a glance from the data that is available, they get some very wonky values for ballistic coefficients because they struggle with disambiguation. And then I found exactly one paper in which someone considers the relative problem, which is what we're truly interested in. And these authors proposed a model-based method in which they estimate the delta from some existing model, Harris-Priester, to the predicted neutral density along a trajectory. Advantages to the estimation alongside orbits are that it's done in real time, right? You're doing this in a column. This is based on readily available orbit data. So essentially, many authors use TLEs, but it can be done with position and velocity for a single spacecraft as well. Disadvantages are that you potentially struggle with low observability, which can be based on your spacecraft's physical dimensions or the orbit altitude or what's happening with the solar activity at that time. So to solve this problem, we're going to take the approach of estimation. And to overcome this low observability, we are going to instead use we're going to base our estimation on relative spacecraft states, which can be estimated much more accurately than absolute spacecraft states, or orbits rather, to hopefully overcome this observability challenge. I'm not going to go into great detail about the filter. I've talked about this before, and we're really short on time. So essentially, the key thing here is that we're estimating absolute and relative orbits alongside absolute and relative effective augmented ballistic coefficients. What I mean by effective is obtain the instantaneous acceleration that this spacecraft is experiencing to drag, because that is something on the scale of like micro or nano newtons. Instead, we're going to get sort of this mean, call it an averaged ballistic coefficient, average augmented ballistic coefficient that a spacecraft will experience over time, which is truly what is needed for control, since drag-based maneuvers can take a very long time. And to estimate the ballistic coefficient, we're going to do this in a model-free way. So we're not using any model. Instead, what we're essentially is that the dynamics of those ballistic coefficient terms are constant in time, and we allow them to be updated through successive observations of the orbit, which I'm going to clarify right now because this is kind of a key portion of the method. So consider a simplified model in which you have only two variables, P and Q, which are the dynamics are there in the upper right. P is a function of Q and some parameter K, and Q is constant in time. At least the model of it is constant in time. Whether or not it truly doesn't matter. As you see in panel 1 of the figure, essentially the filter initially has no knowledge of any relationship between P and Q, and so we just have a circular covariance ellipse there. In step 2, we sample our set of sigma points, and then propagate those sigma points through our dynamics to get to step 3. Now our covariance ellipse shows, interesting, there is actually a relationship between P and Q that we didn't know about before. So the filter now is sort of encoding this relationship. In panel 4, we compute our new mean and covariance, and then sample our next set of sigma points, which give us the predicted measurements. And finally, we arrive at, notice that step 4, which is basically the end of the predict step of the column of the UKF, we still haven't changed the value of Q from our initial estimate, right? There's been no change because we still think it has constant dynamics. So we need the measurement update step in order to incrementally adjust that Q based on an observation. And so that's what happens in panels 5 and 6. We take a new set of sigma points, we propagate, or rather we compute our predicted measurements from that, compared to our received measurement. And now you can see finally in panel 6, we actually, we received a small change in Q based on purely an observation of P. And this is essentially analogous to the relationship between semi-major axis and, well, this is a perfect analogy for the relationship between semi-major axis and the augmented ballistic coefficient. Okay, so, and why do this analysis? Well, basically to illustrate what are the degrees of in this, and there's 2. There's the sensitivity, which is given in this model by K. That's based on attitude, which we control, thankfully, and based on geomagnetic activity, which we don't. And also the process noise covariance, which you can think of as encoding your filter's receptiveness to receiving new measurements. So if you have a very large process noise covariance, your filter is going to think that its model of everything, P and Q, is quite bad, and so it will be very receptive. If you have instead a small process noise covariance, you will updates to Q over time based on observations. And this is something that is unfortunately unavoidable with Kalman filters, where there's a tuning there needed to sort of balance steady state accuracy with convergence time. And if any of you guys were taking 273 this quarter, you're maybe feeling like this, right? Have anyone taken 273 this quarter? Yeah, okay. So you guys are like traumatized, got it. Hopefully you appreciate that. Okay, so I'm gonna just skip this. To set up typically what we usually see, just the only key thing is here, we're talking about 2 CubeSats in Leo and a fixed 10% offset in ballistic coefficient. So this is something that you can expect. No two, even identical spacecraft are not perfect based on variable propellant consumption rates or slight differences in attitude modes. And I'm going to look at varying solar activity, which is an important thing to analyze because that's where model-based methods typically break down. So this is sort of mean solar activity, and I chose as the week that I tested incident when Starlink lost those satellites. So this was like moderate solar activity with a moderate geomagnetic storm, and skipping through the orbit estimation results, which are pretty much exactly what you would expect and look good. Let's get to the drag stuff. So basically you can see, yeah, there's something happening here with the solar storm. So the red line is the ground truth augmented ballistic coefficient, and blue is the estimate of it. And so you can see, yes, we were able to track that storm, and also just to recover information about the drag environment, even without the storm, which is great, right? It's because we were worried about observability. You see, we have nice convergence properties. We end up with errors, something like plus or minus 7% standard deviation on our error, which is great. This is awesome. Relative, again, this is an easier problem because both spacecraft are impacted the same by a storm that happens, when they're close together. But you can see, again, we're able to track this quite well. Errors on the scale and have convergence properties with error in single-digit percent. So that's awesome. We do great during mean solar activity, but that's not a challenge for us necessarily. The challenge is low solar activity. right? Where we have the worst observability possible because atmospheric density is lower. And so here we have a small spacecraft, well, a small low drag spacecraft with a low density atmosphere. And we need to see if we're able to recover useful information from that. And you see in the upper right here, there's no geomagnetic storms during this period of interest, just kind of a typical boring atmosphere during a lull in the solar cycle. And I'm not showing the orbit estimation results because they're basically unchanged. We want to look at what's happening with the absolute and relative augmented ballistic coefficients. And you see performance is a lot worse. Absolute, we're doing something like 20% error. So maybe a 4x, 3 or 4 times worse than we were in the moderate solar activity case, which is expected because we now have a much lower density environment. The induced acceleration is lower. It's less observable. And in the relative case, similarly, we do better than absolute, which as expected, because we have better estimation of our relative orbits, but not as good as we did in the previous scenario where we had higher solar activity. But still able to track. This is still giving us information. I mean, a 12% error in relative augmented ballistic coefficient is still well within what we would use to maneuver. And obviously, it's going to give a significant performance increase over using a static model like Harris-Priester. Okay, last scenario, high solar activity. So we're looking at the St. Patrick's Day geomagnetic storm of March 2015. So this is like sort of this is intense solar activity. How do we do? The answer is really well, which brings me to an interesting observation, which is that this estimation approach based on orbit observations does better of the worst the conditions are, right? Usually you consider high drag conditions to be bad, but from our perspective, it increases our observability, increases the accuracy of our estimates, which is a great result for us. The opposite is true of a model-based method, where when you have normal sort of boring, moderate or low solar activity, your model is going to produce a good value because that's what most of the observations that they're built on were from. Instead, it's these geomagnetic storms, like a spike in the information that the models are not prepared for. So we do great here. We're getting single-digit percent coefficient estimation, which is awesome. Okay, so in conclusion, essentially this method gives us a very lightweight, simple, easy to implement way of getting accurate estimates of this effective augmented ballistic coefficient. Now, remember, we're not tracking the per orbit variations. We don't have a picture of the full profile. We just have this nice kind of smooth curve, which is actually more useful for control perspective. The very next thing I need to do is I need to compare this to some so I can show, hey, this is actually a number, how much better we're doing than Harris-Priester or whatever that benchmark might be. And that's it. Are there any questions?